Good morning, Lars.
Good morning.
Hello. Morning. What time is it in your place right now?
5:20.
Sorry, 5:30. Oh, early in the morning. Thank you for accepting our invitation. Okay.
Yes.
Okay. It's very difficult time to find the time that everybody make convenience with that this situation.
Yes. But we'll make it work.
Yeah. I think you are familiar with Zoom, isn't it?
Yes.
Okay. So I don't have to worry about the operation of the Zoom. You want to operate by yourself, or I can help you if you want to.
No, I think I can do it myself.
Okay. Thank you. Selamat malam, Pak Bob. Mic-nya masih dimatikan itu.
Selamat malam Pak Jarod, sorry.
Ya, ini kayaknya merah-merah ini.
Sumpah Pemuda.
Sumpah Pemuda.
Yeah. Hello Lars, good morning to you there.
Good morning.
Ada Bu Ria nih, Bu Ria, selamat malam Bu Ria, apa kabar?
Selamat malam Pak Ari ya. Pak Ari nanti Pak Ari Rahmadi yang akan mewakili himni kan ya?
J, Pak.
Siap.
Siap.
Oke.
Ini tadi sudah diketik, tadi Pak Ketuanya tadi sudah bilang, Pak Ari, G.
Okay.
Apa yang bisa saya lakukan kecuali bilang ya Pak, siap.
Oh iya, wajib hukumnya kan itu kan. Sebagai kita itu kan bawahannya Pak Susilo kan harus.
Nangge lagi.
Ya.
Pak Sus bilang, tolong ya Pak Ari dibuka. G, Pak.
Oke. 3 menit lagi kita mulai. In 3 minutes we will start the webinar.
Lars, by sometimes next week you'll have a new president or not? Have you voted, Lars? Have you do your civic duty? You still unmute.
Please unmute your microphone.
Have you
I
voted?
have not voted yet, but I will soon. Yes, and whether we'll know at the end of next week, I doubt.
Okay, so you go to the booth or you go by mail vote?
Well, I will fill it out and then I'll take it to and drop it off probably.
Okay, so
Because,
prediction. Who's gonna win?
I think Biden will win.
Really? Oh my
Yeah.
God.
They've changed so many rules at the last minute that there's no way to control who votes and who manufactures more votes.
Okay, that's horrible if Biden wins. You'll be a
Well,
socialist country.
We're mailing out hundreds of thousands of more ballots than there are voters.
Hmm.
And now they're not checking signatures. So you have ballots that are going to people who are dead and somebody picks it up and fills it out and turns it in.
Wow. And those Biden's email scandal does not have any impact. Or Hunter Biden's email scandals.
I don't know. I don't imagine that has a huge impact. I think if Trump wins, it's because people are tired of the lockdown and can't afford to stay locked down anymore.
Hmm.
Okay, I will start.
Time switch. Yes.
Okay. I will speak in Bahasa first in 5 minutes. Then after that, I will use the English. Selamat malam, Bapak Ibu sekalian. Kita akan memulai webinar himni ke-24. Jadi ini ke-24 selama 4 bulan ini terkait prospek pemanfaatan PLTN berbasis Torium. Ini sangat menarik dan menariknya di antara sekitar 470 pendaftar, sebagian besar dari perguruan tinggi. Ini mungkin berkat kampanye Pak Bob terkait PLTT ini luar biasa. Pak Bob itu punya daya marketing luar biasa. Jadi kita akan menggunakan bahasa Inggris dalam webinar ini. Nanti silahkan kalau ada pertanyaan bisa pakai bahasa Indonesia, kita bantu untuk mentranslate menggunakan bahasa Inggris. Good evening, dear colleague, everyone, ladies and gentlemen, and good morning to Lars and dear colleague from Northern America. Maybe you are still early in the morning, and good evening also for our colleague in Beijing and in China, in Shanghai. It's very special today. We have a webinar with the thema about can we use the thorium-based nuclear power plant, or can we use the molten salt reactors? As we know, the molten salt reactor is the generation 4 reactors, has a bright future. So today we have two speakers, prominent speakers. First, coming from the US Torcon, the CEO of Torcon, Lars Jorgensen. And the second is from Shanghai Institute of Applied Physics, Professor Huang. Is the prominent also the speaker of the Torium molten salt reactor in China. So before we begin, as usual, we would like to invite the representative of the Indonesian Nuclear Society, or HIMNI. At this time, we would like to invite Dr. Adi Rahmadi. Please, Pak Adi.
All right. Thank you very much, Pak Jarod. Wah, ini ada Pak Bob. Makasih Pak Bob. Thank you very much for putting this together, Pak Jarod. As you said, that this is a one alternative of technology in terms of nuclear power plant that would be could be beneficial for Indonesia, particularly that the as Pak Bob often say that these things could be built without a state budget, firstly, and secondly, it will optimize the local content. And I've heard that Torcon has been working together with PT PAL as well as with the Ministry of Energy and Mineral Resources to explore this possibility. So I guess on behalf of Indonesian Nuclear Society, I welcome this occasion, the webinar, and of course, I will thank you, Pak Jarod, for putting these things together. I also would like to thank everybody, as particularly the speakers, Mr. Jorgensen from the Torcon company, as well as Mr. Huang from Shanghai Institute. Your presentation would be welcome to this seminar, because this is one alternative for Indonesia, then it could be working for Indonesia. I forgot that I haven't introduced my name. My name is Ali Rahmadi from BPPT, and I'm working for an institution called BPPT. And without further ado, let's have a seminar, and hopefully we can take a benefit from this particular occasions. Thank you very much. Have a good seminar. Selamat malam, Pak. Makasih.
Thank you. Terima kasih, Pak Ari. Before we begin our first speaker, Lars Jorgensen, I would like to say several months ago when we had webinars on nuclear medicines, one of the chairman of the chairman of Medical Doctor of Indonesia said to me, it is better to avoid use the words nuclear. So please find a way. And I remember Pak Bob, he initiated to use the thorium power plant. So this is a breakthrough. Some people, oh, this is one good terms if we want to avoid to use the nuclear. But anyway, as I said, Pak Bob is very good in marketing, in promotion. But we have to know more deeply about the technology of the molten salt reactor by Torcon and by the Chinese, the Shinap. I would like to share the CV of the speaker. The first speaker, Lars Jorgensen, he is the CEO of the US Torcon United States, and he is one of the lead architects of the Torcon molten salt reactors. Lars designed the off-gas system and conducted analysis of neutronic and decay heat active in molten salt research since 2010. Lars is lead technical contributor to the Thorium molten salt reactors public forum. He was graduated on a master from the Stanford University and bachelor degrees from the San Jose University. I think without further ado, I want to ask or invite Lars to give the presentation for 30 minutes. Please, Lars.
Okay. Let's see. There we go. Share screen. Okay, what you see here is a picture of two 500 megawatt power plants with a can sip in between servicing it. That brings in fresh fuel and fresh reactor cores. On top, you can see yellow hatch covers. Because everything is low power, low pressure, we can have very large doors. These doors are 10 meters by 10 meters and weigh about 500 tons. So we can lift those up, and that lets us have access to all the components and make everything accessible for servicing. This is in contrast to a containment that has to contain high pressure in accidents, where you've got a thick reinforced concrete wall with small doors. And when you want to replace the steam generator, you have to cut through the concrete and steel to get to it. So in traditional light water reactors, they tend to try to design things to last forever. We do want them to last a long time, but we have easy access to be able to replace anything if anything does need replacing. And some things like steam generators do tend to need replacing every 30 years or so. How come this is there? Putting this slide up just to remind everybody that the public really doesn't understand about radiation. We have regulatory limits down here at 1 millisievert per year. And it's easy for the antis to make a big fuss if someplace gets to be 10 millisieverts per year, as if that's become very dangerous, because I say it's 10 times the legal limit. So I think when we communicate with the public, we need to be careful to always communicate how far we are away from the danger zone. I mean, it's about 1,000 millisieverts to have acute harm, where you start seeing effects in the very short term, and probably around 100 millisieverts before we see any stochastic effects. So we're a factor of 100 below, and we need to communicate that to the public so that if there was ever any exposure of, say, 10 millisieverts, that doesn't cause immediate panic. For Thorcon, I think most of you have seen something like this, but we're really targeting to get as quick as we can to market. Cost is what drives us. We are not particularly concerned about becoming a breeder and using the minimum amount of fuel. It's really important to have the cost and passive safety so that no operator action or interaction can cause a release. There's no electricity or machinery required to prevent a release. I think that's important, not just from public perception of safety, but also from a cost viewpoint. Because if we can have full passive safety, then the quality and regulatory review of the vast majority of the plant goes away. And we're trying to directly compete with coal for cost. A big topic is, what about the waste? The anti-nuclear activists have made a huge fuss over this, but I think it's important to understand just how much waste we have. If you look at the average electricity use for European or US, it's around 1 kilowatt on average, including industrial use. So if you look at how much that amounts to for 60 years life, that would be about a 60 milliliter bottle of water. So just that's your entire life's waste. And helping people understand how little that is, and therefore how easy we can control it, is an important thing we need to do. If you were to generate that same electricity with coal, you would fill a 4 meter by 5 meter room 300 meters tall, higher than the Gamma Tower. It's the best illustration I can think of to say we generate very, very little waste. Our waste story is actually a positive thing. See, can I make this go away? There. In fact, we added 5 meters to the length of our hull. So It used to be 175, now it's 180 meters long. And right here you can see some tall, thin tanks. That's where we're going to put our spent fuel for 80 years. It's the equivalent of a dry cask storage system. It's air-cooled by natural circulation. So we have an air inlet here and air exhaust there. And it's protected by a 3-meter thick double wall hull that's filled with either sand or concrete. And we can store that until we're ready to do something else with it. By something else, question is, what do you do for very long term? I'm preferring the horizontal drilling method of taking advantage of the technology developed for oil exploration, where you drill a deep hole and then you turn it horizontal and you can put the spent fuel in there. A single small island, in fact, probably a single drilling rig, can handle all the waste from all of the nuclear power from Indonesia, even if you go 100% nuclear. So that just emphasizes how little waste we actually have to deal with. The long-term disposal is actually the responsibility of Baton, as I understand. So this should be taken merely as a suggestion. It's not really a plan. And to be honest, we don't have to have a plan, the complete plan today, because we can store the stuff for 80 years at the power plant, and you can store it longer in dry cask storage if you wish. Another huge issue is the cost. In order to make any big difference, we really need to be cost competitive with coal. If you're talking costs in the $5 to $10 per watt, it just isn't going to be low enough cost to make a big difference in most of the world. On the left, you see a picture of a ship that we designed and built. It's an ultra large crew carrier. It's the largest oil tankers in the world, double hulls. We built 4 of them. They were architected and the construction managed by Jack Devaney. He's the founder of Thorcon. They are almost twice the size of our power plant. And it was built for under $100 million. So that just emphasizes that we have the experience. We know what we're doing on how to build things. We know how to design things so that they can be built easily in a shipyard. And our design is different than the traditional light water reactor with a lot of reinforced concrete, because reinforced concrete does not go well in the shipyards. If I look inside, I can kind of walk through here. Here's the spent fuel storage. This pond here is for removing decay heat, transporting the decay heat to the atmosphere. This is the reactor itself inside here, along with the pumps and everything else that's in the primary loop. So this is where the fuel stays, except when it's being shipped over to the spent fuel storage. Then this is for off-gas storage to let it decay. These pipes, all this maze of pipes, are heat exchangers to take the heat from the reactor core and propagate it down until it becomes steam. And then this section here is the turbine, along with seawater inlet. So there's 3 seawater pumps. We need 2 of them to run at full power. So it's a 3 by 50% plan for the cooling at water. And then you have the generator, and then transformers and the switch yard. We use gas insulated switching gear in order to be able to fit the whole switch yard inside the power plant, rather than having a large area on land that is air insulated. And then that comes up and goes out to transmission lines if we are parked right on the shore. If we are parked further out, then it can also go down and go through a subsea cable. So this whole thing can be built in the yard. It would be built in less than 1 year and on a fixed price contract, which is very different than current nuclear practice. Towed to the site and ballasted down to the seabed and hooked up. We've had our costs validated by DSME, who's the second largest shipyard in the world. So we're pretty solid on our costs. I have a 4-year cycle of cans, because inside of it we have graphite, which does wear out. So we plan on using it for 4 years and then letting it sit and cool for 4 years and then take out the can and replace it. This shows you the primary heat path. You have the pot, which is the reactor vessel, a pump, and then a primary heat exchanger. This all sits inside. We call this the primary loop. Then it goes to a secondary, heat is transferred to a secondary salt. It's also sodium fluoride, beryllium fluoride. We use sodium fluoride rather than lithium fluoride because we haven't seen the availability of enriched lithium-7 on the market yet. If we can get that, we can switch the salts and everything else stays the same, but we don't want to put waiting for the lithium-7 onto our critical path. It means we have to buy a bit more enriched uranium, but it takes out that schedule uncertainty. Then that's goes to what's called a solar salt that's used in solar thermal plants. This is a nitrate salt that is compatible with water. So you have steam here. So the steam generator is from the solar thermal industry. So it is a what's called a helical, but it's really more of a snake pattern to be able to absorb rapid temperature changes. So one of our design goals is to be able to be the dominant power source in the grid. And that means we need to be able to follow loads rapidly. We've designed that in the way that the heat exchangers and the high pressure feed water heaters are designed. They're designed to handle the rapid thermal changes. And then this portion is a coal plant conditions for a turbine generator. These conditions, it's supercritical steam, but they are mild compared to state-of-the-art coal plant. State-of-the-art is probably around 610 C. So the turbine generators we can get from a large number of different vendors, and it's a very competitive market. So that helps hold the cost down for that. That's in contrast to, say, a light water reactor where the steam conditions are unique at 300 C. And so the turbines for light water reactors are custom built for those plants, and they get to have a very high price because of that. This just shows you where it lays out. So here's the reactor core, the pump, the heat exchanger going to the secondary salt with its pump, going to the heat exchanger to the solar salt, which then makes the steam and goes off to the turbine. And here you can see it in context. These would be the high pressure feed water heaters. This gives details on the steam generation side. I'm just going to highlight that we're up at over 47% efficiency if you have 20 degrees C water. It's about 46% if you have 30 degrees C cooling water. So depending on how deep and cold we can get the cooling water, we get different efficiencies, but this is in big contrast to light water reactors, which are around 35% efficiency, which means we need a lot less cooling water, fewer pumps. All of the equipment to transport the heat is similarly scaled down. If you look at the whole power plant, the turbine generator makes up a big portion of it. That's this section right in here. And that portion is going to be directly cost competitive with what's used for coal because we're buying it from the same vendors. Get inside the can. We have the reactor vessel itself. It's not quite spherical, but it's not too far from. It's filled with graphite inside. Salt enters at 565 and comes out at 704. It goes through the pump and the heat exchanger. This is a can for the off gas. We have a flow of helium that comes in through a dry gas seal that flows down. That prevents radioactive gases from being able to migrate up into the motor area. And then that sweeps the xenon and krypton that comes off of the fission process over into this off gas tank. So we have enough storage here for the first week of decay time. We remove about 4% of the salt flow to send to a spray ring to release the off gas from the salt. Xenon and krypton have a very low solubility in the salt, so spraying it does release it. And then that comes out at about 1 liter an hour, and the sweep gas goes by at about 1 to 2 liters per minute to sweep that off and into this tank. So there's a total of 15 cubic meters of fuel salt in the primary loop. We have a makeup fuel tank that's about 2 cubic meters. The fuel in the core is just enough to be critical. So we don't have any burnable poisons. Instead, we add on the order of 1 liter of makeup fuel salt per day. That gets added several times each day. So there's no excess reactivity in the core. We also have about 1 cubic meter of thorium makeup salt to reduce the reactivity. That's important because when you're running the power plant, you're pumping fuel salt out of the core, and you'll lose 200 to 300 ppm of delayed neutrons. When you stop the pump, that reactivity comes back, and we need to add thorium to compensate for that so that we don't get too hot. Down below, we've got a freeze valve, which you can't really see here. The freeze valve is frozen salt in a pipe that is kept frozen by actively pumping cold helium to keep it closed. If you stop pumping the cold helium, the heat capacity of the hot salt adjacent to it is sufficient to open that valve. So if anything breaks that cuts off the flow of helium, we're going to end up opening the valve and draining into these 32 drain tanks. As you can see, they are spread out so that once you're down here, K effective is about 0.5 or 0.6, even if you surround this completely with water. So once it's drained, you know absolutely it is not critical. It will not become critical. The drain tanks are surrounded by an inert gas, probably argon, and then that radiates out to a steel tank wall here, and inside that is 0.5 meter of water. So that'll boil the water and send the steam up the path here through the pipes to a radiator on the bottom here, which will transfer the heat into this water and evaporate that water. There's 5,000 cubic meters of water for a 555 megawatt core. That's about 10 times as much as water as the AP1000 has. That means we have enough water to last us for 165 days. This is at atmospheric pressure, so anybody with a pump can push more water in. And once the 165 days is gone, then there's enough radiating surface here to take decay heat out for the rest of the time. I point out that in Japan, it took them a couple of weeks before they got good cooling to the power plants. So the practice up to that time of having 3 days grace period is just too short. Even in my opinion, 7 days is too short, especially if we're going to deploy these to areas that are less developed. There are no valves that can turn this off, so you can't leave a valve in the wrong position the way that happened at 3 Mile Island. No electricity is required, so a full station blackout won't bother it. And there's no operator error that can block the removal of the decay heat. We do plan on building a full-scale pre-fission plant. We can use that to test all manner of tests. There's no fission, so there's very little radioactivity, but we can use electrical heat and confirm that we do all the necessary cooling and containment. We can even simulate severe tests by adding electrical heat to mimic the decay heat and show that it does indeed remove the heat and that the valves and everything open passively. First step is just to simulate it. This is a simulation we have of the system showing the temperatures in a whole variety of locations in the power plant. We do plan, once we have first run things through simulation and then through the pre-fission plant and then through the demonstration plant at low power and stepping up into higher powers, until we have done this full station blackout with turn off all the electricity instantly, stop the cooling water, no operator action. This is much worse than what happened at Fukushima. And do that with the politicians, the press, and the public present, so that they get not just a reassurance from words by engineers, even the regulator, but that they get to have personal experience and they feel it, I want to say, in their heart. It's not just head knowledge, that the plant will take care of itself and they don't need to do a big evacuation, which, if you look over time, that's been the major harm from nuclear accidents. It has not been the radiation, it's been the evacuations that have caused the most harm. We are designed for cold start, so we have 2 1.4 megawatt electric diesel generators. Those are enough to provide local power to start the auxiliary feed water, seawater, and fuel pumps. Those will drive an auxiliary boiler, which is basically a diesel boiler to provide 50 megawatts thermal. And there's a small century turbine of 15 megawatts. That's enough for us to heat up all the salt and get all the pumps going to start the fission process. So we can start our power plant and bring up the fission island with even if the grid is completely down. That's for a full cold start. Once we're up, if the grid goes down, we can go to hot standby, where the power plant goes to minimal fission power, but we keep all the salt loops moving. And we can tolerate many hours worth of outage and then come back up and ramp the heat up, so we can be the hot standby black start capability that was so wanted for Jakarta in that outage a year and a half ago or so. This is a picture to scale of the power plant, of a coal power plant, and of our power plant, just the heat generation section, not the turbines. The turbines are the same. This is just to give a visual impression that we are a lot smaller, and there's good reason to believe we can be lower cost than coal. Note that coal is what we really view as our competitor, not light water reactors. So we build it in a shipyard, tow it to the site, ballast it down, and then every 4 years come and service it to bring in new fuel. The shipyard initially will be an established shipyard. That is our factory. We don't have to design a new factory and debug it and bring it up the way a lot of small modular reactor plans are. We use the existing shipyards. They've been perfected for 40 years. It's an intensely competitive field, and they've got a lot of surplus capacity right now. So it's a good time to go negotiate with them. We have already talked with DSME, and they are willing to set up a shipyard in Indonesia that would build the power plants. So once we've got the first several built and know what we're doing, we'll bring some people over to train at DSME, and then DSME will go over to Indonesia and build a shipyard there and initially staff the lead positions, eventually being replaced by Indonesian staff and running so that Indonesia builds its own power plants and builds them for export. And I'm running low on time. What you see here is a picture of one person running 4 welding machines. In practice, they really run 80 welding machines, but if I showed you that picture, you couldn't find the person. This is just to emphasize how production-oriented the shipyards are and how they can get work done to build ships at such a low cost. So a good-sized shipyard can build 20 gigawatts worth of power plants per year. Light water reactors, I don't think the entire world could build 20 gigawatts worth of light water reactors a year. There just isn't enough huge foundry space. We're working with the national labs to build sensors and to make salt measurements. Those contracts are getting close to being done now. We've worked with PT-PAL to look to see if they can build the cans and the stuff inside. We believe they have the technical capability. So we still need to work more with them to work out the details on that, but that looks very promising. We think we can hit below 7 cents per kilowatt hour. So we've been talking with PLN a lot about that. Recent progress, well, we went to DSME and confirmed the costs with them as well as Doosan. The steam generator is designed in Denmark and is built for solar thermal plants. That's looking pretty solid. Been working a lot with Materion as the world's premier supplier of beryllium fluoride to work out details for that. We are progressing with the laws and regulations in Indonesia. Bob's been doing great work at moving pieces to be ready. We are in discussions with an international organization for a safety review. And we're just about done with our contracts with the national labs. Okay. That's the end of this part of the presentation. I think I used all my time.
Okay, thank you, Lars. Well, it's very interesting. Your goal is not to be competitive with the pressurized water reactor, but cheaper than coal. It's very interesting. The first thing is, and you also consider, well, based on the proven technology of the experimental molten salt reactor of the Oak Ridge National Laboratory that long time ago, 1960s, I think they operated that reactors. Baik, Bapak Ibu, menarik sekali presentasi Pak Lars ini, bahwa pertama mereka ingin mencapai target lebih murah daripada batu bara, itu merupakan target mereka. Yang kedua juga berbasis pada proven teknologi yang dikembangkan oleh Oak Ridge National Laboratory, mungkin era tahun 1960-an sampai 1969. Saya kira itu menjadi hal yang sangat penting. Mohon ditunggu. Please wait for the discussion. We still have another speakers. We would like to invite Professor Huang. I would like to read his CV first. Professor Hefe Huang, born in 1984, is still young, I think. It's very young.
Thanks.
He has completed his PhD at the age of 27 years from University of Rouen. He's the director of the Material Research Division, Shanghai Institute of Applied Physics. He led the team to carry out the research and development of molten salt reactor structural materials, comprehensive services performance evaluation, establishment of molten salt reactor material standard and specification and the construction of molten salt reactor material engineering database. He presided over 10 scientific research projects and published more than 80 papers in reputed journals. He holds positions in various academic organizations. I would like to invite Dr. Huang, please. The time is yours.
Okay, so thank you very much for the introduction. Okay, I will. So can you see the slide?
Yes.
Okay, so good morning and good evening, everyone. I'm really glad to have a chance to introduce the presentation here. And today the title of my presentation is the progress of the Tmsr in China. This presentation includes 4 parts. So first of all, I will introduce what is the MSR, and then the motivation, the progress, and finally the perspective of the Tmsr. The Tmsr project has launched at the beginning of 2011 by Chinese Academy of Science, and the full name is Thorium Molten Salt Reactor Nuclear Energy System. We call it also the Tmsr. The aim is to develop thorium energy, non-electrical application of the nuclear energy based on Tmsr during coming 20 to 30 years. So this slide shows the Tmsr development plan. We have already finished the mock-up reactor at the end, before the end of 2019. And now we are constructing the test reactor, the 2 megawatt Thorium liquid fuel test reactor. We call it Tmsr Rf1. After we finish this, now we are applying for the funding to support the research reactor. And this reactor should be finished around 2030. It's a 10 megawatt electricity liquid fuel research reactor. And it's also a small modular Tmsr research facility. And finally, it's a demonstration reactor. It should be around 2035. Till now, we have already got a lot of funding from the CAS and also the Shanghai local government. The total funding is around 2.7 billion Chinese yuan. The Tmsr reactor possesses a lot of advantages, such as the thorium energy can be used, the high temperature hydrogen production, the water-free cooling, and also the small modular design. And our Tmsr, the application will focus on the optimized for high temperature based hybrid nuclear energy application, and also for utilization of thorium with prior processing. So next is the motivation for the Tmsr. This slide shows the energy structure of China before the end of 2012. We can see we are more than 620 coal-fired power plants, and the total accounts for about 66% China's of total energy consumption is the coal. So the coal dominates primary energy consumption of China. And also we can see at that moment the wind abundant than in China. Much of the electricity produced by vast wind farm goes unused. The grids enable to accumulate fluctuating source of power and rising capacity in the country's total power generation. From 2010 to 2016, 150.4 million megawatts hour, or as much as 16% of our wind generation was abundant. abundant over the. Sorry, I can't see the slide. Here, the opportunity cost of the wind power curtailment in China is estimated to be exceed 1.2 billion US dollar. So now we pose a solution is the clean energy system. We see the nuclear energy system produce heat and or electricity. The renewable energy system produce electricity and or heat. Both of them can produce hydrogen for energy conversion and storage, which is also used for the lower the CO2 emission and the fuel. This slide shows the overview of the generation 4 system. Actually, as we know, in 2002, they posed there are 6 generation 4 nuclear reactor, but at the beginning of 2016, the US edition has changed something. They removed the supercritical auto-reactor. So now we have 5 type of generation 4. The molten salt reactor is one of the generation 4 nuclear reactor. The fuel cycle is closed and the size can up to 1,000 megawatts. The application is electricity, hydrogen, actinide management. This slide shows the Thorium 232 and uranium 233, the fuel cycles. We can see the mean released neutron number per fission. The parameter eta equal to is the required condition for sustained reactor. From this neutron spectrum, we can see the molten salt, the liquid solution, and the liquid lead can be used for the thorium energy, but the molten salt is the most suitable type because the thorium region is much more the range is much more wide than the others too. The molten salt reactor is suitable for the generate electricity, comprehensive utilization, and the modular design. For example, the thorium utilization, the online refueling, the inherent safety, and out-free cooling. We can see this table. They are list the different coolant, the molten salt, water, sodium, and helium. We can see the outlet temperature. The molten salt is much more higher than others and equal to the helium. The pressure is the lowest, around 2 atm. The heat capacity is much more higher than others, and the compatibility is good. So finally, we choose the molten salt reactor. And another point is MSR has obvious advantage in high temperature comprehensive utilization. We can see the red line, the liquid salt coolant reactor, the MSR, always operate at high temperature. And this high temperature can operate the Brayton application, Brayton circle. So finally, we choose the solution of the low carbon new energy is the high temperature thorium molten salt reactor plus the hybrid energy utilization. Now is the progress of the Tmsr. This slide shows the roadmap of the technology R&D. In recent years, we do a lot of work for the developing the materials science and the chemical science. And we also fabricate to develop the equipment, for example, the reactor components, the pump, heat exchanger, the TH loops. So based on all of these, we have already finished the construction of the Tmsr0. This is the mock-up reactor without fuel. And now we are constructing the experimental molten salt reactor, the Tmsr Rf1. And the next step, we want to apply for the funding from the government to develop the small modular MSR. And the energy should be from 10 megawatt electricity to 100 megawatt electricity. So it's a small modular MSR. We have already carry out a lot of fundamental research, and now in the Jiading campus, we have built all types of laboratory for the MSR technology R&D. For example, the material testing lab, the salt property labs, the irradiation facility, wholesale, and also the super computer. Actually, since 2011, this project has been launched by the CS. We start to carry out widely collaboration with some institute, also belongs to the Chinese Academy of Science, the university, the industry company. And also you can see we have actually before the 2016, we have already carry out a lot of collaboration with the America National Laboratory and famous university. For example, the Oak Ridge Laboratory, the Argonne, the MIT University of Wisconsin. But you see, since the Trump became the president, and the cooperation between China and US becomes very hard. It's hard to continue. So now our cooperation always carry out between the Chinese University Institute and the company. Actually, in the past 5 years, we have made a series of progress for the R&D of the MSR technology. Now I will give you a brief introduction for this. First one is the lithium-7 and the thorium extraction and separation. We have already succeeded in obtaining the nuclear grade thorium high abundance lithium-7 using extraction technology. This includes the high abundance lithium-7 fabrication and also the nuclear grade thorium. We have already obtained all of this. Sorry, the slide is, it doesn't work. No, I can't. Okay, the salt production and the purification. The high purity Flinac batch production, the characterization and the purification has been finished. The synthesis of flab and beryllium control method, we have already built this method and establishing the flab thorium uranium fuel salt thermodynamics database. For the material, first of all is the nickel-based alloy. We have already developed the technology for the smelting, the processing and weld of a nickel-based alloy, the UNSN 10003. We have also developed the Chinese version, is GH3535. And the technology for smelting now can reach 10 tons. and the processing and welding the performance comparable to HASTOLIN. The deformation processing technology for nickel-based alloy with high Molten has been finished. The largest UNS seamless pipe has been fabricated. Now in China, we can fabricate the pipe with the diameter is 168.3 millimeter. This parameter is not right. It's 168. Next one is the nuclear graphite. We are already doing the development of the ultrafine grain nuclear graphite for MSR, involved in the establishment of ASME code of MSR nuclear graphite. In China, at that moment, we have two types of ultrafine nuclear graphite. One is NGCT15, another one is T220. And the pole diameter less than 1 micrometer. That's to ensure the better infiltration resistance than the existing nuclear graphite. And we also establishing the database of its performance and deep involvement in nuclear graphite. So you can see this is the main parameter, the molten salt infiltration experimental results, and also the ASME code provided by us. Normally, the people see the molten salt reactor is a chemical reactor. The corrosion control is a big challenge for this technology. Now, after a lot of research, we have already achieved the control the structure material corrosion by alloy composition, optimization, salt purification, and surface treatment. So you can see it's for the composition optimization. We optimize the composition of alloy, degrade the diffusion of chromium. For the salt purification, we modify the purification technology, control the impurity content. And we developed the FTD coating technology to improve the corrosion resistance. Now we are already solving the corrosion control in fluoride salt. For example, for the GH3535, the static corrosion rate is less than 2 micrometer per year. And we have already finished the R&D of the component, including the salt pump, the freezing valve, heat exchanger, control road test facility, fuel fire loading facility, graphite structure testing facility, pressure meter film, and also the ultrasonic flow meter benchmark platform. The thorium-uranium fuel cycle research, we have already, in this domain, we have already established a thorium fuel utilization strategy in MSR by evaluating the thorium-uranium fuel cycle performance and created a reprocessing flow sheet and demonstrated it in cold lab scale facilities. As for the prior processing technology, the fluorilation and distillation technology has been used for the fluoride salt in cold experiment, and we are already developing the fluoride electrochemical separation technology. For example, for the fluorilation for uranium recovery, we have already verification of the process with in-situ monitoring use of freezing wall technique to mitigate corrosion, delivery from high temperature, and the liquid fluoride melt. The fluoride salt loops, we have already constructed the high temperature fluoride salt loops, developed the equipment to be used with fluoride salt. For example, the pump, heat exchanger, valve, seal, and the pressure meter. Tritium measurement and control. We have already achieved online tritium monitoring. The tritium stripping using bubbling, tritium separation with cell genetics, and the tritium storage. This slide shows the generation description of the Tmsr0. And actually, this mock-up reactor is an integrated facility via scaling method. It is the key facility for the design validation and the license and the simulation for operation and training operator. This is the construction of the Tmsr0. It is a practice for the future test reactor construction. The installation is finished in July 2019, but we finished all of the test at the end of the 2019. The verification experiment of 2 megawatts Tmsr Rf1 design has been done. So this mock-up test reactor, from this one, we to verify the integrative of all of the technology, and also we obtained a lot of experiment parameter from this mock-up reactor to support the Tmsr Rf1 construction. The test the passive residual heat removal system of the Tmsr0. We're already doing the scaling analysis is used to building similarity between Tmsr0 and Tmsr Rf1. The results show that the best estimate value are in accord with experimental data, which support safety license of Rf1. Now the Tmsr Rf1 is a 2 megawatt thermal Tmsr test reactor. It's demonstrated the consumption of MSR with liquid fuel, demonstrated thermal circle and its feathers. It's also one of the platform for the future reactor and thermal circle R&D. This slide shows the main parameter of this reactor. The reactor type is a liquid fuel, and the heat power is 2 megawatts. Temperature, the inlet temperature is 630, and the outlet is 650 degrees C. The life is 10 years. Design lifetime is 10 years. The fuel salt is show like this. We use the U235 enrichment with an enrichment of 19.75. The Thorium is around 30 kilogram in whole reactor, and the coolant salt is a flap. The structure material we use, there are two main structure material. One is the UNSN 1003 alloy, and another one is superfine practice graphite. Both of them are made in China. The system includes the heat generation, the heat transfer, the cavity, including the structure support and maintain, the cover gas and off gas processing system, and also the controlling and instrumentations. This figure shows the fluid parts of the reactor system. Inside of the integral reactor, we have the complete final circulation fluid parts through the reactor core, the primary pump, the salt-to-salt heat exchanger, and fuel piping. The coolant salt circulation system is the secondary loop. The coolant flow path consists of the secondary pump, the salt to air heat exchanger, and the coolant piping. This is the Tmsr Rf1 site. At that moment, in our institute, we have two campuses. One is located in Shanghai, like the star, and another one is the Tmsr Rf1 site. The candidate site is located in Wuwei, Gansu province, about 2,000 kilometers from Shanghai. The annual precipitation is 128 millimeter, and the annual average temperature is 8.3 degrees C. Now, for the Tmsr Rf1 licensing, the site selection work has completed. The site assessment report was approved by the NNSA in December 2018. The PISA report has been reviewed, and the construction license has been approved by the NNSA in January this year. So this slide shows the reactor body of the Tmsr Rf1 is under the ground, around 15 meter on the ground. This slide shows the construction of the Tmsr Rf1 building. We started the FCD on March 29th this year, and we finished the zero flow on July, on the end of July. So you can see this shows the main building of the reactor. And the manufacturing of the Tmsr Rf1 main component has been finished. You can see this slide picture shows the reactor vessel and also the graphite core. All of these key components has been finished. This is the CPM of the Tmsr Rf1 project. This slide shows till the June this year, but the current situation is the main building of the test reactor has been completed, and the equipment installation is in progress. I mean the vessel and the graphite component. So finally, the perspective on Tmsr. The Chinese proposal for Tmsr roadmap like this, based on the technology have made in large scale during last few years. The Tmsr team proposed the roadmap as following: to complete the construction of a test reactor at the middle of 2021, to complete the construction of a small modular Tmsr research facility at around 2030, to complete the construction of Tmsr fuel salt batch pilot process demo facility, and to realize sodium uranium fuel cycle usage based on the three-step strategy by the early 2040. So this is the three-step strategy for the sodium uranium fuel cycle. The step one is the batch process. The fuel is the LEU plus sodium, the online refueling, and the removal of gas, fission products, and discharge all fuel salt after 5 to 8 years. Extracted the uranium, sodium, and salt, FP and MA for the temporary storage. And the next is the step 2 and step 3. Step 3 is step 2 plus continuous process. The continuous process to recycle salt, uranium, and sodium, FP and MA partly separation. So this is our image for the future for the Tmsr elevated hybrid energy park. In this park, we have the Tmsr, the CSP, the solar energy, wind power, molten salt storage, and the hydrogen production. All of this, we will combine all of this to become a hybrid energy park in the west of China. That's all. Thank you very much.
Thank you, Dr. Huang. It's very interesting. The first thing that impressed me is about the roadmap or timetable. In 2030, you want to operate the experimental or demonstration plant for the liquid MSR, and 2035 for the commercial one. And the other thing is about the abandon the wind energies. Yeah, you talk about in a short about the wind. Anyway, we still have time for discussion. I will invite 4 representatives from the audience. The first person is Professor Abdul Waris from Bandung Institute of Technology. The second is Dr. Genirina from Indonesian Nuclear Society. The third is Mr. Yaryanto from Batan. And the fourth one is Dr. Andang from Gajah Mada University. With this various background, I think they will give comments and with their view. And I give for each 5 minutes, and you have to make clear to whom you want to ask or comment. Please, for the first person, Professor Waris. Please, Pak Waris.
Okay, thank you, Professor Jarod. Good morning, Dr. Lawson, and good evening for Professor Hefe Huang. Thank you very much for Dr. Lawson for very important presentation regarding the most readiness MSR design to be constructed for the time being. As we have understood, the Torcon MSR is very unique, very fast fabrication time, built in shipyard and can be carried out directly to the purpose site and so on. I have 2 comments or questions for Dr. Lars. The first, I saw in your site that Torcon molten salt reactor use natrium, beryllium, thorium, and uranium as a fuel composition. This means that you use low enriched uranium as initial fuel. My question, the first is, did you consider to use heavy metal from the present spent nuclear fuel, such as plutonium as a fuel? And the second, as you mentioned in the presentation, Torcon design can be used as ship-based nuclear power plant, and also land-based power plant. If the customer would like to utilize Torcon MSR as land-based, how much money, I mean in percent of original cost, are required? That's my question for or comment for Dr. Lars. And for Professor Hefe Huang, I'm sorry. I think you also have mentioned almost all the problem about molten salt reactor designs and manufacturing component, such as to provide good quality of graphite. As we know, graphite will directly influence the lifetime of molten salt reactor design. If we have a higher power, so the lifetime of the core will shorter, and this, as I mentioned, is directly have correlation with the quality of graphite. And also you have studied about the tritium control, and you have evaluated both Fly-B and Flynex as a fuel salt. My question is, please explain why for the end, at the end of your design, you choose only fly B in your thorium molten salt reactor. And the second one, as we know, one of the big problem from the present generation of nuclear power plant is spent fuel management, such as long life fission product, technetium 99, iodine 129, and cesium 135. One of the options to deal with this problem is to burn this long life fission product in the nuclear reactor. Did you consider in your design to burn long life fission product in thorium molten salt design? I think that's all of my comment or question. Thank you very much for Dr. Lars and Professor Huang.
Okay, terima kasih Pak Waris. Please, Lars and Dr. Huang, you may explain or answer Pak Waris' questions.
Okay, so yes, I confirm that the uranium we use is low enriched uranium. We're planning 19.75% enriched uranium being 15% of the heavy metal, and thorium being 85% of the heavy metal. We are targeting lowest cost and keep it simple, so we're a burner, not a breeder. Could we run on plutonium? Yes, we could. It is a thermal reactor, so fast reactors will make better use of the plutonium, but we generate a small enough volume of plutonium and minor actinides that we could consume all of our own if that becomes a national priority. You asked about, could it be land-based? Initially, we're going to do ocean-based because we have better control over the construction cost and construction schedule. We are very aware that our reputation will depend very much on whether we overrun our budgets and schedule for building the first plant. So we want to make sure we have good control on that. We can build inland. In fact, the initial plan was to do that, but then the schedules have a lot higher risks in them. I think we'll start, and for Indonesia, I don't see a particular reason to ever go away from being sea-based and being able to do it, use the ocean as our railroad. So it can carry very large loads, much larger than we can on land-based. I think that was your questions.
Yes, thank you.
Okay, thank you,
Okay.
Lars. Please, Professor Huang.
Okay, I'm not sure if I can well understand your questions. Thanks a lot for your comments. Firstly, for the coolants, we use at that moment we use the fluoride, and we also add the uranium and thorium into this. But the flint neck we didn't use. We just use it to doing some experiment, to doing some tests.
Thank you.
And for the fission products of the we see the molten salt reactor meet a lot of challenge, especially for the material and also the power processing. And because at that moment we are constructing the test reactor, and the design lifetime is just 10 years, and the fission products, and also, for example, the Torium is also a big problem for the material. The concentration is very low. So at that moment, we don't think about this, don't considering this problem in our test reactor, because the content of the fission products is very lower. But in next step, because we also apply for the funding from the Chinese government to build the research reactor with a high power density from 10 megawatt to 100 megawatt electricity, and the fission products will be a big problem. Now we are because I research about the material, I'm not sure my colleague, the progress of my colleague. I see they are doing a lot of experiment in the lab to doing the separation of these fission products. So I think they have already get a big progress, but I don't know where exactly the details. So yeah.
Okay.
Okay,
Thank you.
very much, Professor Wang.
Thank you, Pak Waris and Dr. Huang. And then the second person who will ask, Dr. Geni, please.
Thank you so much, moderator. My name is Geni. It was very interesting, impressive description from both of our speaker today. And then I want to ask first to Professor Lars about you already mentioned that you will build the, likely this is the NPP 500 mega watt electric, which is sea-based, yeah, and then it will build maybe in the Bangka Island or something like that in Indonesia. As we know that our regulator not yet have the regulation related to the sea-based NPP or something like that. And then you already mentioned also that you already made some calculation that it will be zero evacuation. But I'm wondering, because the Chinese speaker already explained about another approaching regarding to the zero evacuation, and I want to ask you about this one, and also how is the design life of your design regarding to your design. And then second one for the Chinese speaker, thank you so much for your explanation. It is very interesting to us, yeah, if you can share how was your strategy to deal with your regulator, because this is relatively a new technology, yeah, a new
Yes.
technology, and then I think that it will be very we will be very excited if you can share how to deal with your regulator from the zero step until you got the site license and then the polymer. Thank you.
Please, Lars.
Okay, so first off, use the ocean as for transporting the power plant to the site. The power plant is not a floating power plant. It is ballasted and sitting on the ground. Somebody else is talking. I think it's easier if only one person speaks.
Yes, I remove him.
Okay. So we believe that land-based regulation should be appropriate because the plant is not moving. The one advantage we do have is that we can have a thick layer of sand under the power plant, and we can adjust the weight of the power plant on the sand, and that forms a natural seismic isolation. The next question was about a zero evacuation zone. That has already been granted in some cases for US power plants. It is based on whether there's a credible way that you could have a release. Because we're low pressure and because you can't boil the salt, we have 700 degrees C margin, so you don't build up a pressure that's going to push radioactive material out into the atmosphere. The containment then can be steel that's welded and is not under any kind of stress, so it's a very robust and reliable containment. Your final question was on the design life.
Yes.
The design life varies by component. So the graphite is the shortest at 4 years. The fuel salt is 8 years use, and then it builds up enough fission products that we want to retire it. The bearings and such, they're 16 years. The steam generators, probably 32 years. The power plant itself, we're budgeting, assuming 80-year life, based primarily on the idea that by 80 years from now, the engineers better have thought of something enough better that it's time to retire this one, not because it's worn out. So I hope that answered your questions.
Okay, thank you.
Okay, thank you. Please, Dr. Huang.
Okay. So first, I want to see. So sometimes we see the world is balanced. The south.
Kung begitu dapat standar, harus di atas itu.
Really? Okay. The Southeast Asian countries do not have abundant oil and gas resource, but we are generally rich in certain reserves, such as India, China, and Indonesia. Yeah. If in fact, the Chinese government has also paid close attention to the development of the thermal energy in recent years, and has been given a lot of support. For example, the project of the Tmsr. And I think if we can work together to develop molten salt reactor technology and make full use of the thermal resource, I think this should be an important solution for the Southeastern Asia country to clean energy in the future. Actually, in China, firstly, when we start to develop the Tmsr project, we start from the R&D. As I showed in my slide, we're doing a lot of work for the material science and the chemical science research, and develop the key components of all of this. And after we finished all of this in the lab, we want to verify if our technology is okay, and if all of this technology can be combined together. So we constructed the Tmsr0. In this mock-up reactor, there is no fuel. We use the electricity to heat the molten salt, but the other components is the same than the test reactor. So after we success for the operation of the Tmsr0, then we start the real construction of the Tmsr Rf1. So now the Tmsr Rf1 is almost finished. As at that moment, the main building of the reactor is finished, and the key equipment installation is in progress. We want to finish. We hope to finish all of the installation before the end of this year, and next year we want to do some test to finally to reach the 2 megawatt electricity, 2 megawatt thermal. And the next step, we want to continue to support the funding to doing the small modular Tmsr. Why is the small modular? Because we found there are a lot of challenges. It's hard to solve. For example, when the power density, if you're doing the molten salt reactor with a higher power density, then the nuclear irradiation will be a big problem for the nickel-based alloy. You see, there are lots of the helium will be introduced, and then the helium swelling and the helium embrittlement will be a big problem. So after discussion, finally we decided to doing the small modular Tmsr. The power density will be not very high, but all the technology we have can achieve to finish this reactor. So this is our strategy. But maybe in the future we can use directly the small modular Tmsr. For example, 50 megawatts or 100 megawatts. Yeah. Thanks.
Okay, thank you, Dr. Huang. Then this next, I would like to ask Pak Yaryanto, Mr. Yaryanto. Please.
Okay, thank you very much, Pak Jarod, for the opportunity. You can hear my voice?
Yes, please. Yeah.
Okay, thank you. Thank you also for the good speaker. This is very excellent presentation. So I should give the appreciation. Although both of you have the excellent presentation, but you have different approach. Or Mr. Lars or Dr. Lars, maybe you don't need a step-by-step approach to get the commercialization. But for the Chinese, Professor Huang, you explained about your roadmap step-by-step, and I think this is very important to develop that the technology have not proven. So the first, my question for Dr. Lars, yeah. In your design, you use the primary loop and then the secondary loop, still using the sodium salt, natrium, fluor, beryllium, and fluor, thorium. Yes. So why don't use the second loop water? So that is there any influence or effect of the efficiency or not from thermal to electricity? The second one regarding the safety. Do you have any specific to handle the safety of the reactivity and the core? Because in the conventional nuclear power plants, we use such a road control and also for the boron. But how about your design for the reactivity handle? And then to Professor Huang, the first question is regarding the. I see that the progress of your Tmsr is quite significant. Of course, it is supported by your government. How about the government commitment? I mean the national master plan. This is included Tmsr program until the commercialization. So your program or project have been assured from your government. The second is site. Yeah, why you choose the site as far away from Shanghai? So do you have any specific reason? Maybe to avoid the dense population over there, or maybe some things that you have the reason. Okay, thank you very much, Pak Jarod.
Thank you, Pak. Yeah, please, Lars, and then Professor Huang. Please unmute your microphone, Lars.
There. So the first question was, why do we use a sodium fluoride, beryllium fluoride salt for the secondary salt instead of water? If you mix water and the fluoride salt, you get a fairly vigorous chemical reaction, and you'll generate a lot of steam, which expands the volume 500-fold and would present a challenge to the containment system. Our goal was to make sure that the safety was easy to understand and was very robust. So we want to keep the water away from the fuel salt. We don't want to have a heat exchanger that's directly separates the fuel salt and the water by a single layer of metal. So there's always at least two layers, and they're thick layers. They're not the thin layer you have in a heat exchanger. Does this impact the efficiency? A little bit. Yeah, we are at 550 C. We would get somewhat better efficiency if we would go up to 610 C. But it would be a modest improvement because we don't have the large volume of material handling that a coal plant has. We have the same efficiency as a coal plant, even though our temperatures are lower. So we chose the secondary salt to be chemically compatible with the fuel salt, so that even if there is a leak, there's no particular reaction, and it's primarily a matter of detecting the leak, being able to tolerate a small leak, and knowing if you get a big leak. The secondary salt is always at a higher pressure than the fuel salt, so we always leak from the secondary salt into the fuel salt. The second question had to do with controlling reactivity in the core and safety. So the first mechanism for doing that is the thermal coefficient of reactivity. Since we are a thermal spectrum reactor, we do get the advantage of Doppler, and that gives you a big boost for thermal coefficient of reactivity. The second control mechanism is that we can add thorium. So for slower events like slowing down the pump, we can add thorium to reduce the reactivity. We don't add boron. Boron is used in light water reactors because they need a burnable poison, because they put fuel in and it has to last for the next year and a half before they touch it again. So they have to have all the fuel that they're going to burn over the next year and a half has to be there at the beginning. And so it's a light water reactor has a lot of excess reactivity in the beginning that they need to control with a burnable poison. We have no excess reactivity. We add fuel as we need it. The speed of adding fuel is controlled so that it's physically not possible to add it very fast. I think that answers the questions.
Okay, thank you, Lars. And then Professor Huang, please.
Okay. So for the first question, for the support for the Tmsr project, actually, firstly, this project has been launched by the Chinese Academy of Science. It's similar to the one of the department of the China government. And we get 2.7 billion Chinese yuan. But after we finish this test reactor next year, we want to apply for the funding from the National Development and Reform Commission of China. And this is a government department of China. And we apply for around 5 billion Chinese yuan to build, to construct the research reactor. And now we have already applied for the hands up the application document, and we'll wait for the final results. And actually, at that moment in China, there are lots of companies. They are also very interested in the Tmsr project. So they have, they also want to add in this project. So we will see if the government can continue support. It will be better for us. We can continue doing the research reactor. But you see that the company, maybe another choice, like the US, you see there are a lot of the company to doing the molten salt reactor, like Circle and the New Scale, and also I forgot the name, but I see in America there are lots of companies to doing this, and in China maybe in future there are also some company will add in the Tmsr project. And the second question for the site selection, yeah, you see, we choose the site is in Gansu province, and the distance from between Shanghai and Wuwei is around 2,000 kilometers. It's very, very far. Actually, we initially we want to choose the site around the Shanghai, Yeah, but you see, after the Fukushima accident in 2011, and China's government changed the rule, and in the big city, around the big city like Beijing, Shanghai, Shenzhen, Guangzhou, it's forbidden to give you a site to doing the to construct a test reactor. And you see, in China we have three big nuclear power group. They construct and also operate the commercial reactor, and normally the auto reactor. They can get some sites, but we are just one of the institutes from the Chinese academic science. We have not enough power to get a site at the seaside. So finally, we change our direction, and we choose the site in the northwest of the China. You see, because in the northwest of China, there are not so much people there, and there are always sandy land. It's short of water. So you see, we see the Tmsr process some advantage, and one of is the water-free cooling. So we think in the sandy land maybe is a bad choice. It can be a good supplement for the water reactor located in the seaside. So finally we choose in the Uwei. Yeah.
Okay, thank you, Professor Wang. And the last person I want to give response is Dr. Andang Widiharto. Please, Dr. Andang.
Thank you for giving me this chance. I'm very appreciate about MSR, and I have good interest in MSR technology because
yang susun kayu basah sebelum ke Kedi itu kan
the reactor that may very simplest in fuel preparation without any fabrication and so on. It's very simplest, and also MSR can be utilized for closed fuel cycle. I mean breeding, especially for thorium breeding. My question to Mr. Lars is how about the breeding capability of the Torcon design? I mean, is the uranium-233 produced from thorium in fuel can overcome the uranium-235 consumes as the fuel? This is the first question. And the second question is, how about the availability of beryllium? Because I try to browse information. This information usually say that the beryllium is a rare material. So how about the availability of the beryllium? For Mr. Huang, there are some research that try to use other than fluoride salt. Some research use chloride salt, but especially for fast spectrum. My question is in China also conduct some research in other than fluoride salts? Thank you. This is my
Lars.
Okay. So the first question was about fuel utilization. in the fuel, we generate about half of our own fuel, either from thorium becoming uranium-233 or from uranium-238 becoming plutonium. So about half of the fission happens on U-235 that we have to buy, and about half comes from fuel that's generated within the reactor. So we're not a breeder. We don't have plans to become a breeder, but initially, we have to buy about half our fuel. I can see that getting better over time, but especially when we replace the sodium with lithium. But the bottom line for us is cost. Can we keep the cost down? And having a complicated fuel reprocessing plant at every power plant isn't attractive to us. We don't think that's the wise way to go. Second question had to do with the availability of beryllium. Beryllium is not a high demand product today. So there's pretty much one or two suppliers in the world. We have talked with them. They have enough capacity right now to meet our needs. We've looked at how difficult it would be to expand that capacity, and it looks quite feasible. Reusing the beryllium virtually does not get consumed in the power plant. So one can readily distill it and pull it out and reuse it. So we can recycle the beryllium, which would dramatically reduce the beryllium consumption. So I don't see a beryllium supply as being limiting how much power we could produce. I don't even expect it will be limiting how fast we can expand, because I think they can expand their capacity faster than we can. Thanks.
Okay, thank you. Dr. Huang, please.
Okay, actually, at that moment in China, for the Tmsr project, it's just our institute to doing this work. And now we choose is the thermal MSR. But in the future, if it's okay, maybe the fast spectrum MSR is also can be considered. As for the fluoride molten salt, yeah, now in our institute we have also the project for the molten fluoride molten salt energy storage use the fluoride molten salt. Because you see, as I mentioned in my presentation, in China at that moment in the West, the wind energy abundant in China is existed because the wind energy is not very stable. But in our mind, in the future, we can use the molten salt, fluoride molten salt to achieve the energy storage, especially for the wind and solar energy, to change the unstable energy to the stable energy export. Yeah, so we have also a project to doing this. Thanks.
Okay, Pak Andang, thank you. Then I will read some question from the audience. First, the questions from YouTube. There are 41 persons still watching this webinar. There are 2 persons asked the same questions. They ask how long it takes to build commercial molten salt reactor. This question maybe goes to Lars and Dr. Huang. Please answer this, the estimation.
Yeah. So there's two questions there. Is how long does it take to build the first unit, and then how long does it take to deploy additional units? Yeah. The easier answer is how long does it take to deploy additional units? It takes about a year to build the power plant in the shipyard. Build times for the turbine generator is about 18 months. So we think we can build and install a power plant in about 24 months once we have the land and the permits and the construction permits and the transmission lines are available. the more difficult question is, how long does it take before you get your first unit up and running? That will depend in part on the financing. We think the shortest time would be about 6 years, a year to finish up some design and get contracts lined up, a couple of years to build and test a non-fission-based plant, and then about 4 years to build and test a fission-based demonstration plant. But it will be gated by financing and what risk the financing people want to take. They may choose to go with a smaller first step, which would add a few years to the project.
Okay, thank you. Dr. Huang, Professor Huang, please.
According to our development plan, we think maybe 2035, around 2035, the Tmsr can be achieve the commercial application, and we also hope to can achieve this aim. Yeah, according to how to say, it depends on the research at that moment in China. It depends on the continuous funding. If we can get the continuous support, then we hope to finish the research reactor before the end of 2013. If so, the 2035, yeah, we hope and we think it can be get the commercial. Yeah.
Okay. Thank you. And then there is one question from Miss Gloria. She asked about the spent fuel management, how to handle the waste. I think both of you already mentioned during your presentation. Please respond her question about this, how to handle the spent fuel or the waste coming from the MSR. Lars and Dr. Huang, please.
In our plans, the initial treatment of it is simply to pump it into tanks that are inside the power plant and let them freeze and stay there as dry cask storage. That pretty well mimics the plans of how waste is being handled from solid fuel reactors around the world today. Certainly you can reprocess it, and we want to because there's high value material in there, but that is subject to a lot of bureaucracy in controlling proliferation, and bureaucracy can take a lot more schedule than building. So we don't want to put that in the critical path. So we say we'll store it until the bureaucracy gets around to giving us permission to reprocess it. But I need to remind people, it is a water bottle worth of waste for your entire lifetime, even if we do no reprocessing. So don't exaggerate the challenge of dealing with the waste.
Okay. Dr. Huang, please.
Okay. Sorry, actually, I don't know very well for this domain, so I'm sorry I can't answer this question.
Okay. Oh, well, thank you. Is there any storage for some time to store the you have a liquid and solid reactors. So do you think you have like a temporary storage for the moment for the spent fuel?
Yeah, I can understand the question, but because I research about the material, but for the reprocessing and the technology and the design, I don't know very well. Sorry.
Okay, thank you. And there is one question from Mr. Erwin Kasim. Maybe the questions to Lars, but I think it is good to Dr. Huang also respond this question. Based on your experience to build 500 megawatt for the Chinese counterpart is 100 megawatt. This nuclear power plant technology for Indonesia, what is your estimate cost? Well, it's a very frequent question for us because so many people always ask about the cost for this kind commercial 500 megawatt, and for the Chinese is the 100 megawatt, please.
So yeah, Erwin Cosma did type up the question, so he was asking about the surveys and such that need to be done. I believe those costs are in the neighborhood of $500,000 to do the initial surveys of the site and of the grid demand. But that, that's just one step in the process of getting the whole plant built. The question is vague enough that it's difficult to know exactly what cost he was looking for.
Okay, sure. Okay, thank you, Lars. Dr. Huang, please, for your commercial.
In China, I can't give a detailed cost. I can see at that moment, because we have already hand up the application document to the government.
Okay.
As our design, for the 100 megawatt electricity, the cost for the first one, it should be 3.5 billion Chinese yuan. It's around.
I think 1 yuan is about 2,000 rupiah, 2,200 rupiah. Yeah.
Okay, and because our design is a small modular reactor, and we think if we fabricate a lot of with the small modular, and this cost will be reduced. But we will see.
Okay. Thank you very much. Well, there are still many questions, but we have behind the schedule of this webinar. Again, thank you, Lars and Professor Huang, for your time to give us your presentation. And on behalf of Indonesian Nuclear Society, I hope both of you will be successful with the technology for the Torcon and for the Shanghai Institute of Applied Physics also. It's very interesting. For us, for Indonesia, I think, well, this is a big country. We need not only the renewable energy, not only fossil. Inside the nuclear energy, we have many options. We don't have to compete each other between pressurized water reactor, molten salt reactor, or high temperature gas-cooled reactors. But this is very interesting. This is for our future, because, well, according to climate change or the target of the mixed energy of Indonesia, we need nuclear anyway. Again, thank you very much. And well, I want to apologize because there was an inappropriate voice from the audience. Well, hopefully there will be no disturb again in the next webinar. Thank you very much, dan terima kasih kepada Bapak Ibu sekalian atas kehadiran dan kesabarannya dalam webinar ini. Ini menarik bahwasanya Indonesia bagaimanapun juga harus mempertimbangkan banyak teknologi. Kedua narasumber itu menyampaikan dengan cara yang berbeda. Tentu saja Torcon melakukan suatu step yang relatif berusaha cepat, sedangkan China itu melakukan step by step, melakukan beberapa tahapan termasuk menggunakan eksperimental molten salt reactor baru masuk ke komersial. Ini diharapkan memberikan suatu pengetahuan yang bagus bagi kita semua. Tidak memilih, tetapi bagaimana opsi-opsi ini dipertimbangkan. Kita tidak melakukan suatu kompetisi di dalam teknologi nuklir, tapi sebagai negara besar tentu saja opsi entah itu PWR, MSR maupun HTGR atau yang lain itu patut kita pertimbangkan. Terima kasih, thank you very much. See you next time. Bye. Thank you. Thank you, Lars. Thank you. Yeah,
Bye.
thank you.
Thank you.
Thank you.
Bye.
Terima kasih teman-teman semuanya, Pak Bob, Pak Ari, kemudian ada Pak Waris,
Terima kasih.
Terima kasih. Pak Yaryanto dan Pak Andang. Terima kasih, Bapak Ibu sekalian. Semoga sukses. Thank you. Thank you very much, because the participants reaching more than 300 persons, combining between Zoom and YouTube. Ini menarik sekali, lebih dari 300, saya catat 320 peserta kombinasinya. Moga-moga ke depan ada yang menarik lagi, kita mencari tema yang benar-benar yang menggugah kita semuanya untuk tahu. Dan selamat berlibur bagi semuanya, terutama PNS yang mendapatkan cuti bersama, tapi nggak kemana-mana karena takut dengan COVID. Mari.
Terima kasih Pak Jarot.
Terima kasih, mari.
Terima kasih Pak Jarot, terima kasih Bro.
Selamat liburan. Oh,
selamat berliburan. Oh, bos saya selalu ada itu, harus ada itu. Waalaikumsalam, makasih.
Waalaikumsalam.
Selamat malam. Pak.
Mas Farid.
Terima kasih Bro. Sukses.
Pak Susilo.
Ya.
Terima kasih Pak Ketua Umum.
Ya, terima kasih Pak Jarot, luar biasa moderatornya.
Sampai ketemu lagi. Assalamualaikum warahmatullahi wabarakatuh.